All right. Good afternoon, everyone, from the post-lunch hangover. It is my pleasure today to introduce our RAL seminar series speaker, Mackenzie Larson. Mackenzie is a PhD student just down the street at the Department of Atmospheric and Oceanic Sciences at the University of Colorado in Boulder. I'm a CSU alum, but I'll still say go Buffs for her. She works with Dr. Andrew Winters as her advisor and is expected to graduate in May 2027. Mackenzie is both a Department of Energy Computational Science Graduate Fellow as well as an AMS Graduate Fellow. Her dissertation at CU focuses broadly on high-impact weather across the central U.S. and includes three major components. The first part of her work examined extratropical cyclones using self-organizing maps. And the second focuses on downslope windstorms across Colorado's Front Range, which she'll be talking about today. And then the third pillar of her dissertation is the one that I've had the pleasure of working with her on. This last summer, she was a NOAA LaPenta Intern Program Scholar, where she was working on the development of initial conditioning blending capabilities for MPAS, which will be used in NOAA's Rapid Refresh Forecast System version 2. And so again, that'll be the third part of her dissertation. But today, again, she'll be sharing work from the second part of her dissertation, which is on downslope windstorms across the northern Colorado Front Range, which I'm sure is a topic of high interest for those in the room and online as well. So without further ado, here's Mackenzie.
Cool, awesome. Hi everyone, my name is Mackenzie Larson. Thanks Michelle for the nice intro. So yeah, I'm a fourth year PhD student over at CU Boulder in the Department of Atmospheric and Oceanic Sciences. And today I'm going to be talking to you about future changes to downslope windstorms along the Colorado Front Range. And this is work that I've had the pleasure of working with my advisor, Dr. Andrew Winters, along with some folks here at NCAR, including Dr. Jerry Meal, Christine Shields, and Dr. Aaron Doherty. So to start off with, what is a downslope windstorm? Well, if you're from around here, you likely know these are really strong gusty winds that blow down the lee side of a mountain range. So it'll look something like this. And it's often reaching its peak strength near the foot of the mountains, which is right around where we live, and they weaken rapidly as they move further away. And so we care about these windstorms because they endanger lives, they damage property, they disrupt travel, and they also exacerbate our fire weather. So I'm going to talk to you about a few historical windstorms we've had recently, and then we're going to talk about how these windstorms actually develop. So some notable windstorms occurred in January of 1982. Here I'm showing some analog measurements taken at the Table Mesa Laboratory here at NCAR. And then on the right, these are showing damage and peak gust speeds for the whole month of January in 1982, as there were a plethora of windstorms at this time. So looking back at these observations, measurements, you can see on the x-axis, we're going from January 16th to the 17th. And then as you go up on the y-axis, you're getting increases in wind speed. And so during this windstorm on the 17th, there were some overnight winds as well as another band of morning winds. But what was really remarkable is that there was a 137 mile per hour gust measured at NCAR. So these are really strong hurricane force winds. I'm also going to go through, I know it's a little small to see on here, but I'm going to go through some of the other peak gust speeds as well as some of the damage that was observed in January of 1982. Notably, at the Boulder airport, there were 20 airplanes overturned. This is a picture from that. If we go north over to Fort Collins, CSU territory, we have 104 mile per hour gusts measured. If you go up into Wyoming on the 24th of January, we have trailers that have flipped over near Cheyenne. West of Laramie, we then have an 80 mile per hour gust, so lots of damage. These storms are really fast winds. They can impact all of us. And I'm going to show some more pictures of some structural damage taken here by Jerry Meal here in Boulder. There were also some downed power lines outside of the NOAA building over on Broadway. So the 1980s had a lot of really strong windstorms, quite extreme, and more recently we've had some as well. Notably the 30th of December 2021 windstorm that was associated with the Marshall Fire. So this was a really strong downslope windstorm. There was a peak gust of 112 miles per hour measured over at NCAR on the Mesa Lab. And it was really just very unfortunate that a fire was ignited during this downslope windstorm, which makes it quite difficult to put out. And then since the Marshall Fire, we really haven't had as extreme downslope windstorms until this past December, where we had 2 back-to-back on the 17th and 19th of December. If you lived in Boulder, you likely remember because you likely did not have power. Xcel Energy was doing preventative shutoffs as a proactive measure, kind of looking back to the Marshall Fire. So I'm gonna show you now some peak gusts from both of these days on the windstorms. So here is just a map. We're situated here in Boulder. These are peak gusts on the 17th of December, so that first windstorm day going back to midnight. And so you can see at the Boulder airport, we're getting 87 mile per hour gusts. As you go further south, you're in the 80s, the 90s. You continue along Colorado, Highway 93, you're at 102 miles per hour. If we go west into the mountains, we have more 100 mile per hour gusts. So really strong windstorm. Even as those winds start to decrease as they go further eastward, you're still getting 50, 40 mile per hour gusts further east. And even at the airport, they had a peak gust of 63 miles per hour. Then 2 days later, on the 19th of December, these winds come back again. Again, in Boulder, we're at 60, 70 mile per hour gusts, a little bit west of Boulder, 100 miles per hour, and a little bit weaker further out east into the plains in around 50, 40, 30 mile per hour range. But specifically at NCAR, on that second day, on the 19th of December, there was a peak gust shown in this blue line here at around 3 p.m. That was measured at 113 miles per hour. So that's 1 mile per hour higher than what was measured during the Marshall Fire. But what's really important to note about these storms is that these were the first over 100 mile per hour gusts that have been measured at the NCAR Mesa Lab since 2021 during the Marshall Fire. This also set a record for us at CU over on East Campus at our Skywatch Observatory. So here you're seeing gusts again in blue and wind speeds in the red for each day in December. And on the 17th, we set a record of 91 miles per hour measured at our observation site since the site was founded in 2016. So I likely didn't have to really convince you that these windstorms are really impactful for us here, but hopefully that further emphasizes that. And now I'm gonna talk to you about how these windstorms form. There's actually 2 different flavors of downslope windstorms that we experience here along the Front Range, and those are Chinook or fen winds and then Bora winds. So I'm going to start with the Chinook winds. These are our warm downslope windstorms. So I put a little schematic here of a low pressure system that's kind of situated in northeastern Wyoming. We have a cold front that hasn't quite reached northeastern Colorado yet. So our Chinook winds are these prefrontal winds where we're looking for west to northwest flow aloft that gives us this cross barrier flow at the mountains. And so I'm going to show you that schematically now with a cross section. So when these winds come through, we often have cold air that's trapped or dammed behind a mountain range here, so like our Rockies. That allows the warm air above to kind of just skate above that cold air, and it continues until it descends and speeds up at the surface. It also compressionally warms as well. So they're warming and they're speeding up. Another mechanism of getting some Chinook winds here in the Front Range is through orographic precipitation. So when you have some moist air that's forced to rise above some obstacle, like the mountains here, all the moisture needs to precipitate out before it can continue moving, leaving us with dry air that's going to descend and warm. And so if you're ever on 36, sometimes you might see one of those big wall clouds. Those are called fen wall clouds. And this is exactly what is occurring there. And we're just seeing this really pretty cloud while being like blasted by some winds. So in contrast to the Chinook, our snow eater winds, we have our Boras. So these are now our cold winds. So when we have this low pressure system that's now moved further eastward, off to go wreak some havoc over the Great Lakes or do something like that, our cold front has now moved through, and we're usually sitting near the base of a trough or on the western side of a trough axis, and we're now experiencing more northwest flow once this cold front has moved through. And so schematically, the way that this looks now, in contrast to a Chinook, that cold air is no longer dammed behind the mountain range. This depth of cold air, now that the cold front has moved through, now exceeds above mountaintop. And so there's this warm air above. You have this inversion stable air that's essentially capping those winds and forcing them to stay put. So these winds are forced to rise, but they need to go through this small space, so they need to speed up. And they continue to speed up, and then they descend down towards the surface where they warm a little bit, but they're still fairly cool. And so this region at the top of the mountain where you have those winds really speeding up, we're experiencing Bernoulli's principle in action. So as I go throughout this talk, you're going to hear me talk a lot about this stable layer, this inversion layer at the top of the mountain. You're also going to hear me use the phrase mountaintop, which refers to around 700 hectopascals in the atmosphere, and then above mountaintop, which will be around 500 hectopascals. And so we can actually observe these windstorms from soundings when they're taken. So this is a sounding taken from Denver on the 22nd of December in 2020 at 12Z. And this windstorm was quite strong. It made its way all the way out to the Denver International Airport. And we can see that above mountaintop, so we're at 500 hectopascals here, we can see that stable inversion layer aloft. So we see that, and then we're also looking for changes in wind speed, specifically at mountaintop and above mountaintop. We can also see that in the sounding. And this is consistent with previous work from Klemp, Lilly, and Brinkman. That was work that was done here at NCAR. So we know that downslope windstorms are occurring when we have that stable layer. And this is some of the fundamental knowledge that that allow us to better understand windstorms. And that all happened here. So thank you all. So now I'm going to talk about some phenomena associated with downslope windstorms now that we know how they form. One such phenomena is called a mountain wave. This is an atmospheric gravity wave. So here I'm showing our three little triangles for our mountains again, and I'm just showing streamlines for the winds. And so this is when you have air that's forced to rise. It doesn't want to rise, so it's going to be pushed back down by gravity. And it's just going to kind of keep bobbling eastward. And we could actually see this during the Marshall Fire by using smoke as a tracer. So the fire is happening in the lower atmosphere in the boundary layer. It's trapped beneath that surface mountain wave, and you can actually see the wave here. Additionally, if you've seen some of those UFO-looking clouds above the mountains on windy days, those are called lenticular clouds, which can also be observed when you have some clouds trapped in different layers of the atmosphere with these gravity waves. Now, as this downslope windstorm continues to progress, you can have wave-breaking regions aloft above the mountain. Additionally, I want to point out at the surface, specifically at this region, you can get a hydraulic jump. So this is where you have really fast winds at the surface and a really shallow layer of air, where suddenly they get far east enough where they now are able to rise higher, and it causes this big region of turbulence, which you can see here, kind of by water being released by a dam. And this big area of turbulence is called a rotor. This is also a video taken from the Marshall Fire. So you can see on the right side of this photo, you have these really fast surface wind speeds that are stuck down to the surface. They reach part of the atmosphere where they can now rise, and it causes a lot of mixing and turbulence. And so I just showed you some wonderfully artistically drawn figures by me, but we know all of this from previous studies, like Klemp and Lilly in the 1970s that was done here at NCAR. This is a schematic where we're looking at potential temperature from aircraft observations, also in January of 1972. And what we know from here is that by having these close potential temperature contours together, we know that there's a stable layer above mountaintop that facilitates the driving of those winds down towards the surface. They also observed this hydraulic jump and the rotors as well as some other dips in potential temperature aloft as well. So now that we have kind of learned how impactful these windstorms are, how they form, and what are associated with them, I'm going to kind of talk to you about how us at CU, as well as folks at NCAR, got into our research. And so kind of anecdotally, there have been a lot of people in Boulder, like some Boulderites, that have been talking, and everyone's been asking, why aren't these winds as strong as they used to be in the 80s? Why aren't we getting 137 mile per hour winds anymore? So there have been a lot of just folks around Boulder who've been wondering that, as well as scientists at NCAR. So we decided to look into it. So our group looked at downslope windstorms, specifically measured at NCAR at the Mesa Lab from its creation in 1967 through 2024. And this is published right now in a BAMS article called Earth, Wind, and Fire, Are Boulder's Extreme Downslope Windstorms Changing? And it's a really fun read. It reads like a little investigative novel, but I'm gonna walk you through some of the main findings of this paper. And so shown on this figure, we're looking at daily maximum wind speeds for days where gusts are greater than or equal to 70 miles per hour. And so I'm going to walk you through all of the different colors on here, but we're going from 1967 all the way to 2024. You have a wind speed in miles per hour on the y-axis. And so in the blue and the pink, you're looking at observations from Kathy Smith, who works at NOAA. She has a compiled list on a NOAA website that's been taken from storm reports. And the reason why we're using that instead of just Mesa Lab observations is because you already saw an example of one of these analog measurements. There were analog measurements taken from 1967 to 1996. And sadly, these were not digitized, and they now no longer exist. So for this earlier portion of our study, we're relying on Kathy Smith's compilation of windstorms. But post-1996, we now have a new anemometer called the WXT anemometer that's shown in the dark red lines on this plot. And this is now on top of a 2-meter mast that's on top of the NCAR building. And then in 2017, the Gill anemometer was placed back on top of the original 10-meter mast that the original propeller anemometer was put on. And so that was in 2017. So what I wanted to emphasize with all these different types of observations, and as you look just from left to right on this plot, I just want to emphasize that more lines does not mean more windstorms. We can't say anything about windstorm frequency, if they're increasing or decreasing, specifically at the Mesa Lab, because we just have some issues with sampling observations. So what we can actually look at are the winds above 100 miles per hour. And what you'll notice is that as you go from the 60s and 70s towards present day, there have definitely been a decrease in the number of observed gusts over 100 miles per hour at NCAR since the 1990s. So this was the motivation for our study. We wanted to know, why aren't we observing as many of these strong gusts? So I'm going to walk you through a few of the reasons that we talked about in our paper. First, we talked about, is it due to changes in instrument location? Now that we have the instruments that are on top of the roof, the first one was on top of a 10-meter mast on top of the roof, but now we got it replaced by a newer one that's lower. Could there be something going on there? Perhaps. We also have newer instruments that are likely providing maybe a little bit of better measurements. So we acknowledge that there could be some difference with the winds that we're observing over time, just due to different changes in instrument location as well as newer instrumentation. But they are still instruments that are on top of the roof, so they aren't getting as much surface impact. So we ruled that as not a large issue. Anecdotally, we kind of been thinking about how maybe folks in Boulder just haven't been observing as much damage during these windstorms. So there's better building codes now than there were in the 70s and the 80s. For example, when you build a house, you need hurricane clamps on your roof because we get hurricane force winds here. So maybe that's something that could be going on. There's also, what about the roughness length from tree growth? Is there more friction now at the surface, more buildings? Could that be something? We also kind of ruled that out because, again, the measurements we're looking at are on top of the roof of NCAR, so they're quite high. So that leaves us with one culprit. It's likely climate change. So we started to take a peek into this. We wanted to see, how have these downslope windstorm characteristics changed since the late 1960s? And to do this, we took a look at ERA 5 reanalysis data, which is quarter degree by quarter degree horizontal resolution, specifically just wintertime data, December, January, February. And we looked at ERA 5 climate anomalies, so we took the recent time period from 1995 to 2021, when we're observing fewer of those over 100 mile per hour gusts, and we subtract that from the earlier time period of 1967 to 1993, where we're having way more of those 100 mile per hour gusts. So I'm going to show you some cross sections now at the NCAR, or at the Boulder latitude along that. And then you have pressure levels on the y-axis. We're looking at those temperature anomalies, wintertime, from that recent minus historical time period. So the red value means that there's an increase in temperature in the recent time period. And so we're going to go back to our fun triangle mountain schematic. And so what we're seeing here is that this whole vertical layer near Boulder along this latitude is just getting warmer, especially up near the 400 and 300 hectopascal regions. And so what this is telling us is that there's an upward shift in the lower atmosphere vertical temperature gradient now. And so when we pair this now by looking at zonal wind anomalies along this same cross-section, so zonal winds increasing in red, decreasing in blue. Again, if we look specifically at mountaintop and above mountaintop, we see that above mountaintop, those winds are getting much faster, whereas at mountaintop, these winds are now getting a bit slower. So we are seeing an increase in the vertical wind shear, which could also be changing the strength and the structure of these windstorms, as well as how long they're continuing to produce winds. We can look at the zonal, or just the wind speed in general, horizontally instead of looking at a cross section. So this is the same thing of that difference with that recent minus earlier time period. If we look at wind speeds specifically at mountaintop, you can see that for the majority of the state of Colorado, these winds are just increasing above mountaintop level at 500 hectopascals. But now when we go a bit lower, we're finally seeing some blue, and we're seeing that there's actually now a decrease in wind speed right around that mountaintop level. So when we pair that all together, we think that the change in that wintertime base state with the increase in the vertical wind shear as well as the temperature gradient could be contributing to this decrease in peak gust magnitude. But there's only so much we can do by looking at some reanalysis data, especially when these downslope windstorms are really there really aren't two that are alike, and they have some very small differences between them. So we wanted to look at them a little bit more high resolution. So we then began to ask, how would an observed downslope windstorm change in a future climate? Can we use weather models to look at these, look at a little bit more of the nitty gritty to see what's going on? And so that's what I'm doing as part of my PhD project. So the observed downslope windstorm I'm going to talk about today is the 15th of December 2021 Bora. So this is the windstorm that occurred before the Marshall Fire. If you were in AGU in New Orleans, that was going on at that time. And so this is a picture of the high wind warning issued by the NWS Boulder. We're expecting for pretty much the entire northeastern region of Colorado wind gusts ranging from 60 to 80 miles per hour, with especially gusts likely reaching about 100 miles per hour right near the foothills. So there were many trucks that were overturned during the storm, power lines down. But what was really interesting about this storm is that while it was so impactful for us here, it continued moving onward to just kind of being a menace and becoming a serial derecho. And so that's what I'm showing here with some radar and high gust wind reports. So once the low pressure system and the cold front that drove our downslope windstorm kind of moved through, it continued moving to the northeast, causing a lot of wind and tornadoes over in Iowa, Minnesota, Wisconsin. So this is the severe weather outlook from that storm. There were 94 tornadoes associated with this storm on the 15th of December. But I do want to point you to our little blue dots right here along the Front Range where we had our downslope windstorm severe wind events that occurred before this derecho moved through. And so now I'm going to talk to you a little bit more about a synoptic overview of what actually happened during this event, what were the forcing mechanisms and the setup that got us to where we were with our windstorm. So on the 15th of December 2021, this windstorm took place from 14 to 22 UTC, which is roughly 7 a.m. to 3 p.m. Mountain Time. It's associated with a cold frontal passage. It's one of these Bora cold downslope windstorms. So I'm going to show you two surface analyses. This is at 12 UTC, which is 2 hours before the wind started to hit along the Front Range. We have a low pressure system situated over Wyoming, and this cold front extending down to the south, and it's essentially parallel with the continental divide. So as it moves through, we're going to get that nice northwest-west flow, giving us that cross barrier flow for our windstorm. And then if we move a little bit forward to 15 UTC, so this is an hour after the windstorm had started, we can now see that this low pressure system is situated now in the northeastern region of Colorado, and that cold front has now moved through from our region in the foothills. If we look at a little higher levels, we're going to go back a little further in time to 0 UTC on the 15th of December. So this is 14 hours before the windstorm started. Just to give us an idea of what's going on at upper levels, there are 250 hectopascal winds. So the jet streak is in the colored contours in the blue and the purple. There's also wind barbs. And then geopotential height are these black lines. And then I also denoted our low pressure system at the surface. So what's going on at 0Z at this time is we have a trough making its way eastward. We have this low pressure system that is now currently situated on the border of Montana and Wyoming. And if we look down towards the surface, I'm showing surface mean sea level pressure and winds. We can look at the kinking of the mean sea level pressure contours to get an idea of where that cold front is. That cold front is currently over in the western US. It hasn't quite reached Colorado yet. But once we now move to when the downslope windstorm started, 14 UTC, At upper levels, we now see that this trop isn't quite as deep anymore, but it does now have a negative tilt, which will be favorable for intensifying this low pressure system, which is likely why you're getting that derecho as it continues to move out. So it becomes a very powerful storm. But what's also really great, not for them, but for the downslope windstorm, is that these winds now that the trough is becoming a little shallower and it's becoming negatively tilted, is that these winds, as they approach the front range, and you can kind of think as they go down to lower levels in the atmosphere, they're becoming more westerly winds. So we're getting more of that crosswind component, and that, as that low pressure starts to approach Colorado. We can also look at that too, where at the surface, again, looking at the mean sea level pressure, if we follow my cursor here, this is where the cold front would be located right now. So at the start of the windstorm, that cold front has just moved through the foothills. If we go 4 hours later to when this windstorm is well underway, again at upper levels, that trough is kind of going away. It looks just more like a shortwave trough now, and we're really getting a lot more of that zonal flow, which will really facilitate that downslope windstorm at lower levels, and it'll elongate our windstorms as well. At the surface, we can see that this cold front now is extending past Colorado, and it's going to make its way up to the Midwest with those storms. And then now we're going to 2 UTC. This is once the windstorm has completed. While there's still a good bit of zonal flow over the western United States leading into Colorado at upper levels, we now have this high pressure system approaching, which is going to shift our wind direction and cease our winds. If we look at observations from this windstorm, I'm going to show you 3 observation sites. So on the top, you're seeing the measurements from the NCAR Mesa Laboratory. In the middle, you're seeing observations from the Colorado 109 site. So this is if you're driving down towards Golden on Highway 93. It intersects with Road 72 as well. And that's a site known by the NWS forecasters here in Boulder to be like, if a windstorm's going to happen, this site will pick up on it. It's our windiest site. So we often look at that for downslope windstorm identification. And then I also have plots of the Denver International Airport observations just to see how things are looking further eastward. So in the black lines, you're going to see wind speed. In the black dashed lines, you're going to see wind gusts. And then wind direction is in this light blue line. They're all westerly winds on all 3 of these plots, and then temperature is going to be in the red. So close to the foothills at the NCAR Mesa Lab, at 14Z, and this goes to 0Z when the windstorm ends, we can see the sustained wind speed start to pick up to around 10 meters per second, getting up to around 15, and gusts getting as high as almost 45 meters per second. Then as we move a little southward towards Colorado 109, we're pretty much on par with around the same observations. We're seeing now sustained wind speeds a little higher, around 15, 20 meters per second, and then again, peak gusts around 40 meters per second. But what's interesting here is we have temperature measurements for this one. So you can see at around 1430 Z is when that cold front moves through associated with this windstorm. So you can see the temperature immediately drop and the wind speeds start to pick up, which is showing us that that cold frontal passage has moved through. And then if we go further eastward to Denver, you can see the delay of that temperature drop as the cold front moves through because it needs to travel a little bit further. But right when that temperature drops, that wind peaks right up to 25 meters per second. So this was a very strong windstorm that got all the way towards the DIA and out into the plains. So that's why we're using that one to look at. So to further look at this windstorm, I'm using WRF simulations. I'm specifically using WRF version 4.6.1 with 3 nested domains. Those are shown here. So those are going from 9 to 3 to 1 kilometers. And we wanted to make sure that our second innermost domain, the 3-kilometer domain, captured the whole state of Colorado, because as I get further in my analysis, we're really curious about different impacts upstream, and especially looking at those at higher resolution to see how that impacts the downslope windstorm downstream. And then in that innermost domain at 1 kilometer, that's a figure you've already seen, but we wanted to center the highest resolution part of the study right on the Colorado Front Range. A few more WRF logistics. I ran this simulation from 2 UTC on the 15th to 0 UTC on the 16th. Since the windstorm starts at 14Z, it allows for 12 hours of spin up, which you're not going to see in this presentation. And then I also produced 5-minute temporal output resolution so that if we want to compare it more closely with observational sites that are outputting measurements at every 5 to 10 minutes, we can closely match that. I'm happy to talk about other specifications if anyone has any questions about that, but we followed specifications and WRF options similar to CONUS 404, as well as a previous study where I simulated downslope windstorms with WRF. Okay, so now we're gonna look at some results from this initial WRF control simulation. So I'm gonna show you 10-meter wind speed of that innermost domain at 1 kilometer resolution. I have the observation sites marked on here. So as you go from blue to purple, you're getting increased winds. I'm gonna take a sip of water while you look at that. And so this is a really beautiful simulation. We were really amazed at how well WRF was capturing the simulation. It's likely because we picked one that had really good synoptic forcing, but you can see that WRF's producing, surface like mini mountain waves, little gravity waves. You're getting different regions of higher wind speeds, not the same all throughout the entire domain. You can watch it start. All these simulations I'm going to show today start an hour and a half before the windstorm starts, so as they keep looping. And then you can also watch this windstorm start to retract right around 23Z as well. So I'm also going to show you now at the second domain we have at 3 kilometers, a cross section at the NCAR Mesa Lab. Again, wind speed's going to be going from that blue to purple, and you have potential temperature to look for that stability in those black lines. And so as this restarts again, an hour and a half before a windstorm, you're going to see the winds start to pick up right down towards the surface as this stable layer starts to appear and become produced at the top of the mountain. Allows for these winds to really descend down towards the surface. I'm going to let it loop one more time because there's one more thing that I want to point out. We can actually see a hydraulic jump in the simulation as well, right here. You can see potential temperature then increases and the winds stop and you get a little bit more of a turbulent area further eastward of this domain. So this WRF simulation looks really great. It has a ton of detail. We're really happy with it. It looks really pretty, but we can also compare it back to the Klemp and Lilly paper from 1972 where they took observations. We are seeing those tighter potential temperature contours where there's more stability above mountaintop. That allows for those winds to really stay close to the surface and descend along the mountains. We can see the hydraulic jump as well as dips in potential temperature above as well. So now that we know that WRF can really reproduce this windstorm quite well, we can continue moving forward. We can also look at the observations at the NCAR Mesa Lab for like one final check. So this is again 14Z to 0Z, where we have the measurements at the NCAR Mesa Lab in the red from both of the newer anemometers, and then the WRF control simulation at the closest grid point in our WRF simulation to where the Mesa Lab is located is shown here. So we have our winds that are following the same trajectory as they move throughout the windstorm. The WRF winds are a bit higher at the beginning of the simulation, but knowing that the gusts at the NCAR site are usually much higher, we think that this is still a really good reproduction of what the winds at the Mesa Lab. So WRF is doing a great job. So now we can look at this windstorm in a future climate. So to do that, we're using something called the pseudo-global warming or the PGW approach, which some folks here at NCAR also use. And this is where you impose large-scale changes in the climate system to a regional simulation by modifying the boundary conditions. And so our large-scale changes here are going to be the Community Earth System Model version 2 large ensemble, CSM Lens 2 that's also developed here. And that uses the SSP 370 scenario. It has 1 degree by 1 degree horizontal resolution. I'll be using all 100 members. And specifically, we're looking at wintertime, December, January, February data, just like we looked at with the ERA 5 data. And so we're going to impose these large-scale changes onto a regional simulation, which here is going to be WRF, which I already showed the control simulation for. And so the way that this works is we calculate future climate anomalies, again, similar to how we were doing with the ERA 5 anomalies. We're going to take a future time period from 2081 to 2100 and subtract that from a historical time period here, which is going to be 1991 to 2010. So that overlaps in our time where we're seeing those decreased over 100 mile per hour gusts over at NCAR. And we're going to do this for pretty much all the variables that WRF needs to run. We're going to do this for 3D variables such as temperature, humidity, wind, as well as a bunch of surface variables like soil fields, 2-meter temperature and dew point, skin temperature. And we're going to do this and calculate these anomalies for each of the 100 Lens 2 ensemble members. And so I'm going to show you what some of these anomalies look like. I'm just going to show you an ensemble average here. We're going to look at temperature, again along the cross-section of the latitude at NCAR. And so here, it's the average temperature anomaly, so increase in temperature is going to be in red, decrease would be in blue, and standard deviation contours are shown in these black lines. So consistent with what we were seeing with the ERA 5 trend is that everything in this vertical layer is just going to get warmer. Here we're looking at around 5 Kelvin, especially near 400 and 500 hectopascals, with the most variability in this region that I'm circling here, which is right at mountaintop and that above mountaintop layer that we're interested in. Additionally, we can look at moisture, so we can look at specific humidity. And what we see here is that there's more red towards the surface, so there's more moisture in this average future climate with increased variability among lens 2 ensemble members as you get closer to the surface. Next, we can look at zonal wind speed. Here, those winds are now increasing right around jet level, and there's also the most variability in this region as well. So it's likely indicating that there's some differences to the strength and location of the polar jet stream. Can look at meridional wind speed as well. We're seeing actually a decrease of this on the northeastern part of this plot. So again, around jet level, but further eastward. And then everywhere else near the surface is just a slight increase. And so now that we've looked at what some of these anomalies look like, the way that this PGW approach works is that you take these anomalies, or these deltas, and you just add them onto your WRF initial condition data. So here that's going to be ERA 5 data. So you take these lens 2 climate anomalies, you interpolate them to the ERA 5 data grid, and then you just add them together. And from there, you just run WRF, and that gives you a PGW WRF simulation for how the 15th of December 2021 windstorm would look in a future climate. But we do this for all 100 of the lens 2 ensemble members, so there are 100 total WRF simulations. And so we already looked at how the control WRF observations at the NCAR Mesa lab compared with observations. So that control WRF run is shown in the black line. Observations, again, are in the red line. But now I have the average for all 100 of these PGW simulations. And so you can see that we're not getting as many high peaks, likely because it's just an average of a bunch of ensemble members altogether. But we're, for the most part, seeing slightly lower winds throughout the entire simulation. But also what I want to point out, which I'll show you next with some spatial plots as well, is that this downslope windstorm ends about 2 hours before the original windstorm as well. So we have slower winds, and it's also ending early. I can also show you the plot in the gray now, has all the different WRF PGW members. So lots of variability. There's even some winds that get lower than observed winds as well, but really good agreement that these winds are just going to be slightly lower than the control WRF run. So we're now going to take a look at some cross-section plots. So we've already seen this control plot that's on the right, and now the left is going to show the average PGW simulation of all of those 100 ensemble members. So again, we're looking at wind speed and potential temperature are in the black contours. So we can see that WRF is still producing a downslope windstorm. We still get some stability above mountaintop. Winds are forced to descend down towards the surface. We're maybe not seeing as much of a hydraulic jump, but that just might be because of some averaging of all of these WRF simulations. So to look a little deeper at this, we can take a look at a difference plot of that average plot minus control. And so a positive value here means that in the future climate scenario, on average, we're going to see an increase in wind speed, and then blue means it'd be a decrease in wind speed. So there's a few things I'm going to point out as this video continues to loop. Specifically here at the NCAR latitude and further east, we're seeing this kind of blue blob. So we have decreased winds at the surface as well as extending further eastward, which is kind of consistent with what we've been hearing with folks that live out over in Broomfield. You know, maybe the winds aren't they feel like that the winds aren't extending further east as much as they used to. The other notable part of this simulation plot that I want to show you as it restarts again is there kind of feels like there's this second tongue of winds above where we'd expect to see them at the surface. So it's going to descend right here around 19Z. So this makes us wonder if maybe the winds are just being pushed a little bit higher. Maybe that inversion height is just a little bit higher now due to the changing temperature gradient. And these winds are now just a bit higher, and they're not making their way all the way down to the surface anymore. So we can test that hypothesis and look a little further, specifically at 10-meter wind speed. This is that innermost domain that has 1 kilometer resolution. The right is the control simulation that you've already seen with the lovely gravity waves. This one on the left, again, it's an average. It's not going to have as much detail. But what you're going to see, which is consistent with what we saw with the plot of wind measurements at the NCAR lab, is that you're not seeing as much purple. The winds just aren't quite as fast anymore. And you can see the retraction earlier of this downslope windstorm, where it's ending about 2 hours earlier. And we can also see that on a difference plot. So winds decreasing in the average PGW simulation will be shown in the blue. And you can see this big swath of blue further eastward, kind of parallel along Broomfield area. And that's comparing with that blue blob that we saw. It's showing us that there's this decreased eastward extent of these surface downslope winds. And then as the windstorm starts to end, you can see it retract earlier than the control simulation, where the downslope windstorm's ending 2 hours earlier. So to kind of look at this a little bit easier without things moving all the time, I'm going to look at when the control wharf simulation produced the maximum wind speed at the NCAR Mesa Lab grid point, which was at 1725 UTC. And we're going to look at these screenshots throughout the rest of the presentation. And so here again, we're seeing that reduced wind speed at the surface near NCAR as well as further east. So if I pair that with a 10-meter wind speed plot, we can see that, all along further east from the foothills, we're seeing a decrease in wind speed. So maybe the mountain wave is no longer extending as far anymore, or it's that we have those higher wind speeds aloft now. So we're seeing this decrease in maximum 10-meter wind speeds along this innermost domain. We can now go back to our looking at mountaintop levels as well as above mountaintop. So if we look at 650 hectopascals at our 3-kilometer domain, specifically I want you to focus on near the NCAR latitude. We can focus on right upstream of NCAR. There are some decreased winds right at mountaintop. So that's going to have some impact there. And if we go a little bit higher now to 500 hectopascals, again, looking along that NCAR latitude, we're seeing, some white, maybe not really huge increases, but as you get, further upstream, there are definitely some increases in wind speeds above mountaintop. So if we add that all back onto our schematic, we're seeing slower wind speeds at mountaintop, as well as faster wind speeds above mountaintop. So just like we were seeing with the ERA 5 data, we're seeing an increase in vertical wind shear, except now that has a larger magnitude. Next, I'm going to show a cross-section of temperature, again, still with those potential temperature contours. But I have the yellow showing warmer temperatures, and then blue are going to be colder temperatures. And so it's a little difficult to see what's happening. So we're going to look, again, at a difference plot. Everything's just red. Everything's warmer in the average future climate scenario, which is what we expect to see. That's the climate anomaly that we added on, but we're also just expecting to see the whole climate warming. But I do want to point out one part where that's kind of second tongue of the wind starts to kind of descend the mountains above the surface. You can see the associated compressional warming associated with that right here at around 21Z. So if we look back at our schematic again, we talked about the wind shear. We now have the warm column, again, similar to what we saw with ERA 5. So we can look at, finally, just the cross-section of specific humidity and talk about some of the moisture. So moister air is going to be shown with blue here, and drier is going to be shown with some yellow. So as this reloops again, an hour and a half before the windstorm here, you're just seeing at the surface lots of moisture. That anomaly that we had all the moisture at the surface, and we are definitely seeing that here. So this is likely going to have some latent heating implications. We definitely want to look further upstream to see if there's more precipitation, what impact that has on these windstorms. So that's in our future work. Again, another quick difference plot. Green means that things are more moist in our average PGW simulation, and everything's just green. Lots of moisture. But when you have that kind of second tongue descending with the air compressionally warming, it's also bringing it down that dry air aloft, which we can see signals of in our simulation right around 20Z right here. So to kind of just put it all together, warmer, wind shear, moisture, especially down towards the surface. So we're seeing this increase in moisture below approximately 500 hectopascals, which is our above mountaintop region that we really care about. So to just wrap up, we talked about how there's now an upward shift in the lower atmospheric vertical temperature gradient that is likely impacting windstorms, along with the increase in vertical wind shear at mountaintop and above mountaintop. And there's also moisture below, there's increase in moisture below 500 hectopascals, which is likely causing some influences that we haven't looked at quite yet. So we want to know why all these things are happening, and it's likely, I hinted at this at part of the presentation, we think that there could be an increased depth of the mountaintop inversion layer. So if the area that the winds need to funnel through is now getting taller because of the increased vertical temperature gradient, the winds don't need to descend quite as fast down the mountain, and that would also explain why they're not getting as far eastward as well. And then also there could be changes in moisture or precipitation upstream that are having some diabatic effects that will impact things further downstream. So in summary, we used the PGW simulation for the 15th of December windstorm to see how that specific windstorm would look in a future climate. I talked a lot about, specifically at the surface, we're seeing a decrease in maximum 10-meter wind speeds further eastward of the foothills. And so future work is really looking at that mountaintop inversion layer as well as mountain wavelengths and looking at some other upstream, downstream effects. Okay, I know I'm like running out of time, but Michelle told me I should do this. So I'm looking for a job. I graduate in a year, and so I would really like to collaborate with folks or work on proposals or work as a postdoc. So I'm just gonna, shameless plug, real quick, speed run. If you like wind stuff, besides the BAMS paper and the second chapter, I have another paper on downslope wind verification of the National Blend of Models. That was as part of my Noah Hollings internship. My first chapter of my PhD is published, where I looked at Lee cyclones along the central US and created an updated climatology, and I used machine learning for that. I like modeling, so I like using MPAS, breaking MPAS, trying to look at initial condition blending to replace partial cycling with an MPAS, which will be the new dynamical core for the RFS version 2. Yes, we did it. But before I finish, I just want to say thank you all for everything that you do in the uncertain world we have today. So we all really appreciate it.
Never used this before. Anyways, thank you, Mackenzie, for an excellent talk. Much appreciated and very timely given a potential downslope wind event soon. We can open it up for questions. Does anybody in the room have a question? Right.
Hi, thanks for the interesting, nice analysis. So I'm wondering if you look at the fruit number. Fruit number relates, it's the wind speed, terrain height, and the Valsalva frequency, which describes the vertical profile of potential temperature. My guess is that the fruit number also changes. Maybe it becomes weakening at the mountaintop. So I'm not sure if you have any plots to show the fruit number.
Yes, that's a great question. It's funny because as you asked that, my advisor, who's like 2 rows behind you, smiled because last week he's like, you should look at that number. So that is on my to-do list. And yes, I want to look at that. I want to look at the inversion layer, try to look at like the front Valsalva frequency as well. I'm trying to figure out how to quantify some of that inversion and stability.
All right, Jared, we'll go to you and then we'll go online to James.
Okay, great. Great talk, and I especially loved your visuals and animations and everything. That was awesome. So my question is more like, so for the WRF simulation for the control run, what did you use for the initial conditions? Was it ERA 5?
Yes.
Did you see whether using her analyses, for instance, would have been better, since her has the resolution, high resolution of the terrain, whereas ERA 5 kind of smears that out? Might her have provided better initial and boundary conditions for this particular event?
Yeah, I definitely think it could have. When I originally started on this project, I was actually using North American regional reanalysis, NAR data, but we decided to go with ERA 5 data to match the BAMS paper to make it more consistent with that. And we were quite impressed by how well WRF did. So I think it'd be interesting to still run it with her analyses.
All right, I'm going to go to James online and then we'll come to you. So James asked, while downstream moisture increases in PGW, I'm curious what relative humidity looks like at low levels along the Front Range, since that is another key factor in promoting wildfire conditions.
Yes, let me see if I made these plots. Let's see if I kept them on here, but I don't think I did. Yes, I did not keep them on there. They are similar. There's a little bit more of some variability as well. Mostly what I'm thinking, I briefly looked at those plots. There's a lot more spread amongst the ensemble members with relative humidity than any of the other variables that we saw. So when I was showing the different standard deviations on the plots, and they didn't look too crazy, and when you actually plot that with the WRF simulations, that one had the most difference, the most variability. So I think there's a lot of uncertainty with how that will impact downslope windstorms. But I have made those plots, but I haven't looked into them deeply, but I can do that. That's a great suggestion.
All right, thanks again for the talk. I have so many questions, I'm struggling to pick one of them. But if I recall from downslope windstorm theory, the vertical profile of wind can be really important on whether or not a downslope windstorm can form or not. Mm-hmm. So I remember like an environmental critical level being some factor of vertical wavelength essentially being important. Have you looked into whether or not there have been changes there and how that impacts? Because I know the mountaintop level inversion layer is just one factor.
Yes. Yeah, I think I have not looked into that yet. I'm like just scraping the surface. It was a lot of, I'm trying to figure out how to deal with like 100 WRF simulations. I've never had to do that before. So it's like a big data problem that I've never had to do. But yes, I do want to look at that. I'm thinking back to like Dale Duran's papers, who also works on this project with us. I think that's another great way to look at it. So I'm loving all these ideas. Thank you.
Yeah, he would be good. Yeah. And I think your comment on the diabatic heating upstream, I think that's probably actually really important.
Yes, I agree.
Maybe even more important than any changes in static stability.
Yes, I agree. And Dale Duran also agrees. He thinks that's very important.
Hello. My question is, so you have this 100-member PGW ensemble, but are you only comparing against one single control run, or do you have an ensemble for the control?
Yes, only one control run for right now. We've talked about kind of using some more of the more recent kind of historical lens 2 data sets, but more like CSM lens 2, but like now, and trying to run an ensemble with that to get some of the variability there too. But
yeah, because that would be useful because, I suppose you were comparing these kind of, when you were talking about, say, these wind speed magnitudes, you were comparing against, I guess, the average PGW, and so it's maybe unsurprising that the control is so much stronger, a single control member is so much stronger than the averaged approach. So I think what you just suggested would be actually very complementary, or at the very least alternatively looking, partitioning like a subset of some of those really strong PGW members that did actually reproduce some much stronger winds and see what was different about them. I don't know.
Yes, I would love to do that. Yeah, I definitely want to parse like the stronger and weaker and look into some of those specific characteristics. Yeah.
Okay, great.
Yeah, thank you.
All right, we'll go online, and then Maria, I'll come down by you. The esteemed Jeff Beck asked, how high above the ground was the lowest WRF model level above the NCAR wind observations?
Oof. I have not exactly looked at the exact level. I previously ran one where it was at the lowest level that I looked at was the 33 meters, which went across the right where the building should be. So, but I need to double check for this simulation how low.
Maria, how much
Thanks,
do you
Jeff.
trust me? No.
So this is building on James Pinto question. I was thinking about the fire indices and whether that is actually increasing or decreasing the fire weather potential, because you're decreasing the winds close to the surface, you're potentially increasing the humidity, but you're also increasing the temperature. So it would be very curious. Like, it's not a question that I think we're going to have an answer to, but like just to calculate one of the fire indices, for example, the hot, windy, dry, to like all of your ensemble members to see how that would be changing with. Yeah.
That's a great idea. Thank you.
All right. I think we have time for another question.
All right, so I guess first I'm going to echo Jerry's comment that your visualizations are really, really cool on here.
Thank you.
And I had a question about one more potential visualization. Did you have any comparison SKUTs of the control and the ensemble mean for the PGW? Because it might be a little bit easier to see where that inversion is setting up.
Yes, I have not done that yet for this study, but a previous study I have done that. So I will absolutely do that. It's a great idea.
Okay, cool.
I've got one more. All right, so Jonathan asks, very thought-provoking seminar. Could you speculate on some of the other factors that may also be changing due to climate change, such as changes in the position of the jet stream and orientation strength of troughs? Did you look at these in reanalysis to see how these may be changing as well?
Yeah, I haven't looked at that too much personally. Our group does a lot of jet stream research. So I think what will be really interesting, someone actually asked me this the other day at a public speaking event, that if the jet stream's migrating further poleward, how is that going to impact these windstorms? And so as we kind of talked about with these Bora windstorms, they're really synoptically driven with these cold fronts. So if the jet stream's migrating further northward and we're not getting as strong of low pressure systems and cold fronts, I think we could likely expect to see weaker windstorms, fewer of them perhaps. Same thing with if the waviness of the jet is changing, if you're getting decreases in strength of these low pressure systems and associated fronts, I do think that will directly change these windstorms. But we have not looked or quantified that yet.
All right. Give a couple more seconds for any late-breaking questions. All right, well, Mackenzie, this has been excellent. Thank you so much. And Mackenzie will be hanging around this afternoon, so feel free to stop by FL2 and try to avoid the construction. But she'll be hanging out, and feel free to also reach her on some of her contact information there. So thank you very much, Mackenzie.
Yes, thank you.